So in this video, I wanted to walk you through problem 1 of the chapter 6 homework. So we have a relatively simplistic truss. It consists of only 3 members. It's loaded by a downward vertical force applied at joint A in the truss, and it's supported by 2 supports which act directly at joint B and joint C. We noticed through examination that the support at joint C is a roller, meaning that the reaction associated with that support will be purely in the vertical direction. And although the support at point B is a pin, meaning that that support structure can oppose both horizontal and vertical forces, or another way to say that is that its reaction will have an unknown horizontal and vertical component. Because this truss, when it's viewed collectively as a rigid body, is only loaded in the vertical direction, we'll see when we enforce horizontal equilibrium that the horizontal component of the reaction at B is 0. So how are we going to go about doing what the problem asks us to do, which is to use the method of joints in order to determine the force in each member? Remember that the forces acting upon the members themselves are viewed as internal forces from the perspective of the truss, and whether or not these members are in tension or compression. And we know that that's just going to be a function of whatever assumptions we make when we draw the free body diagrams and apply statics of particles to each joint, whether or not the quantities turn out to be positive or negative. So just walking through the approach, remember that in order to do this, if you were to try to apply the method of joints at any of those joints directly, you would end up with a statically indeterminate problem. For example, if we were to try to actually draw a free body diagram of joint B, we would notice that it's acted upon by the force in the members BC and BA, namely whatever force is exerted on those members by Newton's third law, as we'll see a little bit later, we can relate to that the force that the member exerts on the actual joint. So since if we were to analyze any joint directly individually first, we would get a statically indeterminate situation. What we need to do is enforce equilibrium on the entire rigid body of the truss. In order to do that, we'll separate it from its support structures at B and C. We'll replace the effect of those support structures by reaction forces, which have a nature that we discussed earlier. Namely, we don't know the vertical component of the reaction at Cy, namely how much the roller is actually pushing up on the truss to counterbalance this applied force P pushing down. And similarly, we have unknown vertical reaction at B and an unknown horizontal reaction at B. So how can we go about solving for these quantities? Well, as we mentioned earlier, it's trivial. If you sum all forces in the x direction, we know automatically that the reaction at B, although it could oppose horizontal forces, it's not doing so in this case. So how we would determine the two individual vertical reactions, which are counterbalancing this applied force in the downward direction? Well, we've done this quite a few times now. All that we need to do is to enforce rotational equilibrium at either point B or point C. I chose to do it at point B. What that basically means is if we pin this truss at point B, notice that the downward force P is going to rotate it in the clockwise direction. That's counterbalanced by the reaction at point C, which induces a rotation about point B in the counterclockwise direction. So using our traditional counterclockwise direction positive sense for summing moments, we find that, as we mentioned, the reaction at C in the vertical direction is going to induce counterclockwise rotation, so it is positive. The perpendicular distance from a vertical line of action to point B is 400 millimeters. I chose to work in SI units of 0.4 meters. So 0.4 times the unknown force Cy that we wish to solve for, minus, since the rotation that force B induces about point B is in the clockwise direction, the perpendicular distance from the line of action of P to point B is 900 millimeters or 0.9 meters. So that's 0.9 times whatever your P value is. These two things have to offset each other and be 0. If you solve that for the unknown reaction Cy, you'll find out that basically Cy is the ratio of 0.9 to 0.4 times whatever P value you're given in your problem. I was given 1600 newtons, so that comes out to be 3600 newtons. Now I can easily solve for the unknown vertical reaction at By by simply enforcing vertical equilibrium on the entire body. Basically what this equation says is that whatever portion of the applied downward vertical force P hasn't been picked up by the vertical reaction at Cy, that's how much By has to consume. So in this case, it turns out to be minus 2000 newtons, which means that this pin is actually pulling the truss down, which it has to do because if you think about this external loading, it would induce a clockwise rotation about B. So Cy, in order to counterbalance that, has to be up. And in this case, because of the various magnitudes, because P is so far away, it has such a large lever arm from point B, this pin at point B ends up pulling the entire truss back down. So you do your math here, you solve for your two unknown reactions, and now you can go joint by joint and draw a statics of a free body diagram of a particle, and in four statics of particles, which you have two equilibrium equations, sum of all forces in the x and y direction being equal to 0, and you can solve for any unknowns that you have. So working here at point B, I draw a free body diagram of the actual joint B. I know that the reaction at B is 2,000 newtons in the downward direction for my value of P. I always assume consistently that the members are pushing in on the joints. You can do it as them pulling away on the joints. You just want to be consistent. That way you can let the mass speak for itself in terms of the signs. Notice by Newton's third law, if a member is pushing in on a joint, that means that the joint is actually pushing out on that member. If the member is not moving, there must be an equal and opposite force by Newton's second law on the other side. Long story short, what actually happens here is, and that's why I put the compression here over the tension. I worked this whole problem trying to rush it this morning. I thought I would get all of these done in the morning, and I got about 45 minutes into doing this, and then my day got away from me. And this is the first free time I've had since then. So if you assume the sign convention that the members are pushing in on the joints, what that means, as you see here, is that that member would be in compression. So if these quantities turn out to be positive when we do our free body diagrams and enforce equilibrium, the members are in compression. So how would you do a decomposition? You can do a force triangle, and that's a lot of text that you see in statics when you're doing statics of particles. They do force triangles. Sometimes that can be a little bit easier. I chose to actually do a decomposition where I said I could, FBA has an unknown magnitude, but I know its direction is along the line of action of that member. So I could do a decomposition if I just knew this quantity theta. And I know the geometry of that member is associated with this type of triangle where I have a vertical decline of 375 millimeters and a horizontal shift of 900 millimeters. So I can solve for the hypotenuse of this triangle, 975 millimeters, and from that get expressions for the sine of theta and cosine theta. So this is something you've done a ton of times now thus far in statics. So that allows you to decompose the unknown force in the member, FBA, in terms of sine theta and cosine theta, which we've actually computed there. So all I did is I expressed each of the three forces in rectangular form. FBA, of course, has an unknown magnitude. FBC has an unknown magnitude, but because of the geometry of the truss, it's purely in the negative I-hat direction. And BY we know is purely minus 2000 J. So if I sum all forces in the X direction, basically what I see is that there's a relationship between the unknowns FBC and FBA. In order to solve that, I have to sum all forces in the Y direction. And basically what's going on there, if you think about it, because the reaction at B, sorry about that, is pulling this pin down, the force that member FBA exerts on the pin is the only thing that can pull it back up. So you can kind of naturally see that the sense that we've assumed for the force that member BA exerts on this pin is going to be incorrect, because it's the only thing that can have an upward Y component, and that upward Y component is necessary to offset this downward Y. So not surprising that when we do the math here, it turns out that FBA is negative. And remember, as we said here, going back to the top of the free body diagram, if a member pushes in on a joint, that means that the joint pushes out on the member. So the member is in, for the sense convention that we've assumed, if the quantity turns out to be positive, that means that this member is in compression. However, in this case, we knew in advance that it wouldn't be. It has to be negative in order to basically pull that pin back up. So that means that FBA is actually in tension because the native sign convention assumes it's in compression. When you go through and solve for FBC, that means FBC has to turn out to be positive, 4.8 kilonewtons. And remember our default sign convention, if something is positive, it is in compression. So you can use that same technique, and you can enforce the method of joints on either joint A or joint C and solve for the only force in a member that we haven't computed yet, which is FCA, and use that same approach. You can do a free body diagram on this joint or a free body diagram on this joint. This is probably going to be the little bit of an easier one, although they're technically the same number of forces in both cases, because here you don't forget to include that external vertical force. So hopefully that makes sense, and I will see you all in the next video.